Dear students, welcome to sowdaambikaa group of schools. Now, this topic deals about that dimensional analysis. That's a small topic. One question you should be come from that, a NEET or a JEE. One question you should be come. So listen, before enter into the dimensional analysis, a small basic idea. So what are they? So first is that physical quantity. Physical quantity. First, the definition for physical quantity. So what is the physical quantity? We know all the substances are made with the help of that tiny particles called atom. Now, is a matter. Any substance occupies some space, it is called as that a matter. But we didn't know that the quantity of that matter. It is a small quantity or large quantity. So we have to need that measurement. So before study about the measurement, you should know what is called as that quantity. So it is a physical quantity. So definition for the physical quantity as a quantity which can be measured. The quantity, physical quantity that can be measured. That's a measurable one. Then it is derived from that a law of physics, in terms of which law of physics and described is called as the physical quantity. So the physical quantity, that's a quantity that can be measured, and in terms of, listen, in terms of which law of physics and describe. So such a way we can classify all the physical quantity under the two different parts. So first of all, fundamental physical quantity. All the physical quantities comes under the two categories. First, that is a fundamental physical quantity. Then another one is a derived physical quantity. Then second, derived quantity is a fundamental quantity, that is a derived quantity. Fundamental, what are called as that a fundamental quantity? A quantity cannot be expressed in terms of any other physical quantity. Fundamental is a base. Fundamental quantities or basic quantities. Fundamental quantities, there's a quantity, they cannot be expressed in terms of any other physical quantity. So cannot be expressed in terms of any other physical quantity. And there is a base, there is a fundamental, there is a basic quantities. We cannot express in terms of any other physical quantity. Then what are called as a derived quantity? Derived quantity that can be expressed. That can be expressed in terms of fundamental quantities. In terms of fundamental quantities. So that is the definition for that fundamental physical quantity and the derived physical quantity. That's the definitions you have to understand with the help of some example. So what are they? Some of the examples for the fundamental quantities. There are 7 fundamental quantities are there. Only 7 fundamental quantities are there. So one is the length. Length is the fundamental physical quantity. We cannot subdivide this. We cannot multiply. Is a length. Mass. time is that temperature. Then current, electric current. Luminous intensity and amount of substance. Amount of substance. Amount of substance and luminous intensity. Look at that. Length, mass, time, temperature, electric current, amount of substance and luminous intensity. These are the 7 fundamental physical quantities. Using these 7 fundamental physical quantities, we can be express any other physical quantity. They all comes under the category of that derived quantity. Say for example, start from that small physical quantity, area. Area is the derived quantity because we can express in terms of fundamental quantities. Area, the formula for the area, the expression is area is equal to length into breadth. Length is that one quantity, breadth that is also a one quantity. So already first beginning what I say, the quantity, physical quantity that can be expressed, that can be measured. The which quantity we can measure is called as the physical quantity. So length we can measure is in a centimeter or millimeter or meter or kilometer we may measure. So breadth that is also one form of that length. So length into breadth, that is the expression for that area. So area is the derived physical quantity because it can be expressed in terms of fundamental quantities like length and breadth. Such a way volume is equal to length into breadth into height, or otherwise area into height. Area into height. So more number of derived physical quantities are there. So in this lesson we are going to see about that fundamental and derived quantities, and using that how we study about that dimensional formula. The dimensional formula in physics which are used for how many purpose. That is the usage of the dimensional analysis. So today topic we are going to see about the dimensional analysis. Before that we are going to see about that fundamental quantities and the units of fundamental quantities. Units and the symbol of fundamental quantities. Listen my words clearly. Physical quantities, fundamental physical quantities and the unit of physical quantity, symbol of physical quantities and the dimensional formula for physical quantities. Look at that. First I am going to write the unit symbol for the fundamental quantities, fundamental physical quantities. So first is the length. Length is the fundamental physical quantities. The unit of length is a meter. A meter. And now it is the unit. Symbol. Symbol. The meter that is denoted by small m. So small a. Meter. Then mass. The unit of mass is kilogram. The symbol of mass, that is that kg. That's a symbol. You should understand. It's a symbol. This is a unit. It is a fundamental quantity. Then time. Second, the symbol for time is that S. is a symbol. Then temperature. Temperature, the unit for temperature is Kelvin. It's a Kelvin. The symbol is that capital K. Symbol is a symbol. It's a K. Then current, electric current. Electric current is a ampere. Ampere, that is the unit for that electric current. The unit is that A. Then amount of substance. Amount of substance. Here is a mole. Mole is a unit. The symbol is that MOL. And the last one is a luminous intensity. Luminous intensity. Here candela. Candela, that is the unit for that luminous intensity. Here that is that CD. Now we see about that fundamental physical quantities and their units and symbols. From this we have to easily understand the dimensional formula for these fundamental quantities and also easily understand that dimensional formula for the derived quantities also. Now I am going to see that dimensional formula. It's a dimension. Dimension for that fundamental quantity. So first of all, we consider what is the dimension. Here is a fundamental quantity, it is a derived quantity. It is a derived quantity, area and volume. The powers. Now we see about that is the area, volume. And also in our textbook they are giving that velocity. So I am written that velocity. Velocity. The formula for that velocity is displacement by time taken. So displacement divided by time. Displacement, that is in the form of length. So the unit of displacement is that meter. The symbol for the displacement is a m. So the symbol for displacement is m divided by the symbol for the time is a second. So it is a s. Meter is that fundamental unit for the quantity length, but meter second inverse is the derived unit for the derived quantity. Derived unit. It is a fundamental unit. Fundamental unit for fundamental quantity, derived unit for derived quantity. Such a manner, what is the derived unit for area? Here, the unit for length is a meter. The unit for breadth is also a meter. So meter into meter, that is equal to meter square. Meter square is a derived unit for derived quantity. Likewise, here the unit for area is the meter square. Then height, that is also measured in terms of meter. So that is equal to meter cube. Meter cube is the derived unit for derived quantity. So that is the understanding about that what is the quantity and units. It is a derived quantity. These are the derived units. These are the fundamental quantity. These units are the fundamental units. Fundamental units and the fundamental symbols. Now, dimension. At the time of express the derived quantities, at the time of express the derived quantities, we should be raise the powers of fundamental quantities. the power of quantities. Say for example, velocity is equal to displacement divided by time. So the unit is a meter second power minus 1. Meter and seconds are the fundamental quantities. The powers of fundamental quantities which we have to raise: meter power 1, second power minus 1. Meter is a fundamental quantity, second is also a fundamental quantity, but these total unit represent the derived quantities. So the powers which we have to raise, so dimension, so dimension. Now I am written, so I am going to write that derived quantities in terms of fundamental quantities, in terms of powers of fundamental quantities. Listen, velocity is the derived quantity. Now I am going to written this derived quantity in terms of powers of fundamental quantity. These are in terms of powers of fundamental quantity. Velocity is a derived quantity. Meter second inverse, that is the powers we have to raise in terms of fundamental quantities. So for the dimension for length is L. Dimension for length is L. Dimension for mass is capital M. As like the dimension for the time is a capital T. The dimension for temperature same is a capital K. Dimension for electric current is that ampere, so capital A. The dimension for amount of substance is a mole. The dimension for luminous intensity, that is a CD. These are fundamental quantity, that is the fundamental units, fundamental quantity symbols. These are the symbols for fundamental quantities. Now the dimension for that fundamental quantities. The dimension you should be represent within a square bracket is a L. M is the dimension for mass. T is the dimension for time. A is the dimension for temperature. Then ampere is the dimension for that electric current. Mole is the amount of substance. This is the dimension for that luminous intensity. Now, the dimension is nothing but any other physical quantity. Now it is a derived quantity. These are written in the form of fundamental quantities. Raise their powers. The powers of such a fundamental quantities we have to raise to represent the derived quantity. After substitute this dimension for meter and second inverse is a meter. The dimension for meter is a L. So that is equal to M is replaced by L. And the second inverse, second dimension for the second is a T. So T inverse. Now it is the dimension formula for velocity. Velocity is the derived quantity. Now we are returned to express that derived quantity in terms of fundamental quantities. So what? The powers of that fundamental quantities we have to raise. Why? To express that derived quantity. That method is called as the dimension. Now these are the dimension for that fundamental quantities. As like we are going to see about the dimension formula for some derived quantities. Already we see about that area. Area that is equal to length in the bracket is a expression. It is a quantity, it is a expression. Clearly watch, because that's the beginning. It is a expression. It is a unit. And symbols. So length into breadth. So it's a meter into meter. So that is that meter square. Is a dimension. It's a dimension. Dimension meter. L is the dimension for meter. So we have to written L square. L square is the dimension for that derived quantity area. Like volume, length into breadth into height, or otherwise area into h. So area is a meter square, and also h is also in meter. So in meter, meter square into meter, that is a meter cube. So the dimension for that volume is L cube. So that's a starting for the dimensional analysis. So area is a L square is a dimension for area, L cube is a dimension for volume. Then next is a density. The expression for density is a mass by volume. Mass by volume. So now it is the expression mass by volume is a formula also. So that is equal to mass. The unit for mass is kilogram. So kilogram divided by volume. The unit for volume is a meter cube. Now it is the unit for density is kilogram per meter cube. Now I am going to write the dimensional formula for the density. How we write? The dimensional formula for kilogram is a m. The dimensional formula for kilogram is capital M. So capital M divided by a meter cube. The dimensional formula for meter M is the L. So that is equal to L cube. It may be written as M L power minus 3. Now it's a dimensional formula for that density. It's a density. Then force. Force is also a physical quantity. That is also a derived quantity. The force is equal to mass into acceleration. Mass into acceleration. Mass into acceleration. Then mass kg, then acceleration. So before see about the acceleration, first we saw that velocity. Velocity. Velocity is equal to displacement divided by time taken. Displacement divided by time taken. So the displacement, the unit for displacement is a meter. Time, that is also second. So meter second inverse. Now it is the unit for that physical quantity velocity. Then the dimensional formula meter. Dimensional formula for meter is a L. The dimensional formula for the second is that T. So T power minus 1. T inverse. It is a dimensional formula for that velocity. Then acceleration. Acceleration. Acceleration is equal to velocity divided by time taken. Because the definition is the rate of change of velocity. Rate of change of velocity is called as a acceleration. So already what the unit for that acceleration is that already unit for that velocity is that meter second power minus 1 divided by second. Now the compound unit is meter second power minus 2. So the dimensional formula for acceleration is L t power minus 2. Now it's a basic step. See, that's the beginning. So this time you have to clearly understand about the dimension. So area, volume, density, velocity, acceleration, these are the fundamental quantities. Now we are express that fundamental quantity in terms of their fundamental quantity. Derivative quantities are expressed in terms of fundamental quantities at the time we have raised the powers. That is called as a dimension. The powers which we have to raise the fundamental quantities to express the derivative quantity is called as the dimension. These are the small example. Then force is equal to mass into acceleration. Mass, the unit for mass is that kilogram. Then the unit for acceleration is a meter second power minus 2. Now that is the unit for that force. Unit for force. The dimensional formula of the force is, dimension for kilogram is a m. So m. The dimension for that meter is L. Then the dimension for the second is a T. So T power minus 2. Now it is a dimensional formula for force. It is a dimension formula for acceleration. It is a dimension formula for that velocity. Dimensional formula for density. Dimensional formula for volume. Dimensional formula for area. That's the beginning to know about the dimension. Okay. Then next we are going to see about that what is a dimensional formula and a dimension expression. For small understanding, I will going to explain. We may write this velocity. The velocity we may written as Lt power minus 1 or Lt inverse. Lt inverse. We may write L power 1 T power minus 1. What's the meaning? It is deals about that dimension. Dimension. That is a represent that fundamental quantity. Fundamental. We may written as that same velocity m power 0 L power 1 T power minus 1. The powers which you have to raise, it is a derived unit, derived quantity, physical quantity. The powers which we have to raise in terms of fundamental quantity. M is the fundamental quantity, L is the fundamental quantity, T is the fundamental quantity. To represent that derived quantity, the powers to which the fundamental quantities are raised. For why? To represent that derived quantity is called as the dimension. Clear? That's the definition. You have to understand. Then dimensional formula. Dimensional formula. In our book, to explain the dimensional formula, they are giving the acceleration. We already see about the acceleration. So acceleration is equal to velocity divided by a time taken. Velocity divided by time taken. The unit for the dimension formula for velocity is a L T power minus 1 divided by time is a T. The dimensional formula for time is a T. So that is equal to, if the denominator comes to the numerator, the power should be inverse. So L T power minus 2. Or we may written as that dimensional formula for acceleration is m power 0, L power 1, T power minus 2. Okay. These are the fundamental quantities, the powers which we have to raise. How many fundamental quantities and which They are represented with the help of that dimensional formula. How many fundamental quantities? Zero fundamental quantities of mass. In acceleration here there is no one quantity for mass. So that is called as the zero quantity of the mass. How many? Is a plus one quantity of the length minus two quantity of the time. Such a way, how many and which fundamental quantities are needed to express that derived quantities are called as the dimensional formula and also called as the dimensional equation. So in this page they are giving that idea about that dimension, what is called as a dimension and dimensional formula and a dimension equation. So clear? These are about that introduction for that dimension. Then in our textbook they are giving which physical quantities are having the same dimensional formula. So in a textbook, our one more question, which physical quantities are having the same dimensional formula? The question is torque and energy. We have to going to check the torque and energy, they are having the same dimensional formula or not. Now first, what is called as a torque? Torque is a physical quantity. Torque is nothing but is a rotational force. If you consider a disc that will be fixed about their axis, at the time of applying the force, that is start to rotate in an anti-clockwise direction. Applied force, the force is applied here, but the object is fixed within their axis of the rotation. Now the torque is the twisting force or rotational force. How we find out the torque that will be applied on the body? Torque that is equal to force into distance between application of the force to the point where it will be fixed. Now it is the distance R. So the torque is equal to force into perpendicular distance, outer distance. So force is a physical quantity, a distance that is also a physical quantity. We may return the physical quantity in terms of the fundamental quantity. How? Force is equal to mass into acceleration. So force is written as mass into acceleration into the distance d. Then mass, the unit for mass is kilogram. The unit for acceleration, is meter second power minus 2. And the unit for a distance is a meter. So the unit for torque is equal to kilogram meter square second power minus 2. Now it is the unit for the torque. Then fundamental units. Now it is converted into the fundamental units. Kilogram is a fundamental unit. Meter is also a fundamental. A second is also a fundamental. The derived quantities is written in the terms of fundamental quantity. Now there is a dimension. The kilogram dimension is a m. Then the meter square, meter, the dimension for the meter is a L. So L square, the square. Then the dimension for the time second is a T, T power minus 2. It is a dimensional formula for the torque. Torque is a force in the distance between the application of the force to the point where it will be fixed. Likewise, energy. Now what is the dimensional formula for energy? If both the dimension for the torque and the energy are same, we said that both the physical quantities are having the same dimension. How we find energy? you may easily understand energy, kinetic energy or potential energy. Kinetic energy, the formula for this is a well-known expression. Kinetic energy, that is equal to half mv square, or otherwise the potential energy, that is equal to mgh. You may know very well about that in the lower classes. Is that kinetic energy and potential energy. Now, what is the dimensional formula for that energy? Kinetic energy of mv square. Now I am going to substitute that dimensional formula for that units. Of is a mere number. Number does not have the dimensional formula. So then m, mass. That's that is a m. M is the mass. So the mass, the dimensional formula for mass is a m. And v square, v is a velocity, L t power minus 1 whole square. That is the dimensional formula for the mass, and that is the dimensional formula for velocity. At the time of simplifying, m, at the time of squaring, that is a L square and t power minus 2. That is the dimensional formula for energy. Look at that, the dimensional formula for torque is a dimensional formula for the torque, is a dimensional formula for the energy. So these two physical quantities are having the same dimensional formula. That's a one mark question that will be present in our textbook. We may check mgh, potential energy, that is also having the same dimensional formula. How is a mgh? Mgh, m is a mass. I don't think that is a meter, it is a mass. So that's the dimensional formula for mass is a capital M, is a g. G is the acceleration due to gravity. The dimensional formula for acceleration is L t power minus 2, and h is a height. So the dimension, that is a L. So after simplification, m L square t power minus 2. So we measure either that will be a kinetic energy or potential energy. All the energies that should be having the same unit and the same dimensional formula. So in this question, the torque and the energy only having that same dimensional formula. Next, at the time of enter into that next level, you should know that dimensional formula for the fundamental quantities. That is very useful for easy go through. Okay. So till we study about that, what are that dimensional, what's the dimension and what's the dimension formula, and what is called as a dimension expression. Then the physical quantities are mainly classified into two categories. One is a variable, then another is a then physical quantities are mainly, that is classified into two types, constant and variable. And now we are going to see about that constant and a variable. Physical quantity, they are classified into constants and then variable. Constant, they are classified into two types, dimensional constant and a dimensionless constant. Dimensional constant, dimensional constant, dimensionless constant. Dimensional constant and a dimensionless constant. Likewise, variables also classified into two types, dimensional variable. Dimensional variable, here is a dimensionless variable. Now the dimension is classified. So what are the quantities are having that dimension, they are comes under the category of the dimensional variable and dimensional constant. Those physical quantities does not having that dimension, these are comes under the category of the dimensionless constant and the dimensionless variable. Now we are going to see the examples. Say for dimensional constant. Here gravitational constant and a Planck constant. Gravitational constant. Gravitational constant. The value for gravitational constant, that is equal to 6.67 into 10 power minus 11. Newton meter square kilogram power minus 2, that is the unit. How they are find? How we find the unit for the gravitational constant? Now the expression that is present in the inverse square law. So here the force between the two planets in a heavenly objects. Now the two massive substance. R is the distance between the two substance. Now the force of attraction between the two masses, F is proportional to is a M1 is a M2. Now R is the distance between the two masses. F is proportional to M1 M2 divided by R square. At the time of replacing that proportionality constant, we should introduce F is equal to G into M1 M2 divided by R square. Now it is a gravitational constant. Look at that. How we find out the unit for the gravitational constant? Here G is equal to F into R square divided by M1 M2. Then the unit for force is a Newton. Newton. How we derive the equation? How we derive the unit for the gravitational constant? The unit for force is a Newton. Equivalent unit is also there. First is a Newton. Then distance or distance. The unit for R is meter. So meter square divided by M1 is the mass of the first body. M2 is the mass of another body. So mass, the unit for mass is a kilogram. The unit for M2, the mass M2 is also a kilogram. So kilogram into kilogram, that is equal to kilogram square. So if it will comes with the numerator, the formula is a Newton meter square kilogram power minus 2. So the constant which have the dimension is called as the dimensional constant. So if it has that unit, you should have the dimensional formula also. So what is the dimensional formula? Newton. Look at that. As a Newton, that's the unit for force. Force, F is equal to M into A. So Newton, as a unit for that force is a Newton. Equivalent unit is that mass, kilogram. Acceleration, meter, second power minus 2. Now the equivalent unit for that Newton. So if you substitute that Newton, kg, meter, second power minus 2, here is the meter square, divided by, here is the kilogram square. Cancel that kilogram, kilogram. Here is the meter cube. So the unit is that meter cube kg inverse second power minus 2. Now it's the unit for that universal constant. Then dimensional formula m kilogram. So m power minus 1 L cube. Then second, so t power minus 2. Now is the dimensional formula for the gravitational constant. Are you understand? It's a small example. It's an expression. From this expression, the gravitational constant G is equal to F R square divided by M1 M2. Then I am going to substitute that individual units and the dimension for that derived quantities. So that's the dimensional for the gravitational constant. Here the constant value is 6.67 into 10 power minus 11. So that will be having the constant value and dimension. So constant value and dimension. Which quantities are having constant value and dimension? These are comes under the category of the dimensional constant because it has a constant value and it is also having the dimension. Okay. So gravitational constant, it will comes under the category of a dimensional constant. Gravitational constant. Okay. Just likewise, another one example is a Planck constant. Planck constant. Planck constant. Planck constant, that value is 6.626 into 10 power minus 34 joules second. Now it is a constant value. Then it is a unit. Okay. Planck constant. How we get that unit? The two equations are there. One, lambda is equal to h by mv. It's a de Broglie wavelength. That one is the equation. Lambda is equal to h by mv. The another one equation is E is equal to h nu. Here h is a Planck constant. H is a Planck constant. So h is equal to lambda into mv. Then lambda is the wavelength. Wavelength is measured in terms of meter. So the unit for wavelength is a meter. M is the mass and velocity. The product of mass and velocity we may represent such as the momentum. So mass. Then mass, the unit for mass is a kilogram. Then V is the velocity. The unit for velocity is meter second power minus 1. So the unit for the Planck constant is meter square, kilogram, meter square, second inverse. It is the unit for Planck constant. Here is the energy. The unit for energy, SI unit for energy is a joule. So H is equal to E by nu. It's a frequency. So that is equal to energy. The unit of energy is a joule, and the frequency is that second inverse. So it may be written as joule second. That is also equivalent unit for this. For writing that dimension, that one is very easy. So what I am writing this unit. So now I am going to convert dimension in the unit. Now I am going to return dimension. What we write? The dimension for kilogram. Kilogram, that is a mass. So the dimension for kilogram is a mass. So I am going to return m. Then is a meter. Is a length. The dimension for length is a L square. Then the dimension for the time is a T. Dimension for the time is a T. But the unit for time is a second. So what we have to carefully watch that words. So a T power minus 1. Now it is the dimension for that Planck constant. This constant should have the value, constant value, and also having the dimension. So it is also comes under the category of the dimensional constant. So another one is the Planck constant. That's all the explanation for the gravitational constant and the Planck constant. These are the dimension. In our textbook, the dimensional formula, the two questions are there. The dimensional formula for the Planck constant and the gravitational constant is a separate 1 mark question. So note that dimensional formula for the Planck constant. In previously, that is the dimensional formula for that gravitational constant. So let's solve. Then we see about that dimensionless constant. Dimensionless constant, they are having that value only, numerical value only, values, but they doesn't having that or did not have that dimension. They didn't have the dimension. Why they didn't have the dimension? That is explained with the help of the example. Say for example, pi. Pi, we know about that. Pi is equal to 22 by 7. Numerical value only. R that is equal to 3.14. They have the values only. Numerical values only. But they didn't have the dimension. No dimension. Likewise, exponentiation E. This value of E is merely equal to 2.7. It is also does not having the dimension. A constant doesn't have the dimension. These all comes under the category of the dimensionless constants. So the constants are classified into two types, dimensional constant and dimensionless constant. So these are the examples. Likewise, we are going to see about that variables. Why we say that is a variable? Velocity 5 meters second inverse, 7 meters second inverse. If a ball that will free fall towards the downward direction, first the acceleration is at 2 meters second power minus 2. So after a few seconds, the acceleration is 5 meters second power minus 2. Then 7 meters second power minus 2. Lost 10 meters second power minus 2. When it will be fell down, the downward direction, the acceleration will increases. So the acceleration is a variable, it is not a constant. Look at that, the values are increasing order. If you throw upward, the acceleration that will be going to be reduced. So that is also variable. The acceleration, area, the area for that given room is different. In our house, all the room different areas. So the area is not a constant quantity. It is a variable physical quantity. Likewise, volume is a tank size or the substance if you have take, the volume is different for the different objects. So these are the variable quantities. Then likewise, force, momentum, work, power, energy, surface tension. Look at that, all the physical quantities are the example for the variable physical quantities. In a variable which are having the dimension, these are called as the variable dimensional quantities. Is it more quantities like that? Area, volume, density, pressure, force, like that, etc. Work, power, energy, etc. Here, all the quantities are does not having the constant numerical value. It is a varied depending upon the time. So that is called as that variable physical quantities. They have the values and also they have the dimension. They are the variables. If they are having the dimension also, it will come under the category of that dimensional variable. These are the example for the dimensional variable. The variable which does not having the dimension, these are comes under the category of the dimensionless variable. What are they? Why they are didn't have the dimension? Both the numerator and the denominator, they will be having that same unit, same quantity. They will be cancelled out. Then specific gravity. Specific gravity is nothing but density of the water, the density of the substance. Density of substance divided by density of water. That's a formula for the specific gravity. Look at that. Here numerator is also the density, denominator is also the density. The formula 2 units are cancelled out. If any one of the quantity having that numerator and denominator having the same unit, they are cancelled out. Finally, this quantity does not having the dimension. This quantity does not having the unit. So specific gravity does not having the unit. Then strain. Strain, changing dimension to the original dimension. Dimension, change in dimension to the original dimension. Dimension, they are get cancelled. Lengthwise, linear expansion, here is also linear expansion, they are get cancelled. Then if the expansions are volume wise, here is also volume wise, so they are get cancelled. Or area wise, bulk modulus, rigidity modulus, like that. So the strain, change in dimension to the original dimension, both the numerator and denominator should be having that same units, so they cancel out. Then another one is the refractive index. A refractive index. Refractive index, the formula is that Ca by Cm, velocity of light in air divided by velocity of light in a medium, or lambda A by lambda A. Velocity, wavelength of that light in a air by wavelength of light in a medium. Or otherwise, that is equal to sin I by sin R. Angle does not have the dimension. Does not have the dimension. Angle. There is no dimensional formula for the angle. So, because the angle theta, sin theta is the opposite side by hypotenuse. Opposite side, that is also a centimeter or millimeter or any one of the meter. Then hypotenuse, that is also in a meter. So both the numerator and the denominator, that will be having the same unit. So all the angles does not having that dimension. So the refractive index does not having the dimension because both the numerator and the denominator, they are having the same quantity. So that is a small topic. It's a physical quantity. They are classified into constant and variable. Constant, dimensionless constant and dimensional constant. Likewise, dimensional variable and dimensionless variable. They are explained with the help of the example. Then homogeneity. What is the homogeneity? It's a small question. One more question that will be present in our textbook. Homogeneity of dimension. Homogeneity of equations. Homogeneity, that means uniformity. All the terms in that equation, that should be having the same dimensional formula. This equation is said to be a homogeneity. Let's say for example, all the terms, say v square is equal to u square plus 2as. That is the only equation. That is the equation of motion. One small equation. So v is the velocity. The v is nothing but velocity. U is also a velocity. It is a initial velocity. That is the initial velocity. A v, that will be considered the final velocity. Here a is the acceleration. S is the displacement. So these are the physical quantities. After applying that dimensional equation or dimensional for the given derived quantities, all the terms are having the same dimensional formula. At this time, the equation is said to be a homogeneity. How? And now it is the velocity. What is the dimensional formula for velocity? Dimensional formula for velocity is L T inverse. Now it's a v square. So it's a dimensional formula for velocity. Then it is a square. Listen, that's important. That is equal to initial velocity u. then LT inverse power 2 plus 2 is the numerical value. Numerical value does not have the dimension. Then acceleration LT power minus 2. Then displacement is also denoted by that length. Dimension for length is a L. Now I am applying that dimension for all the physical quantities. At the time of squaring this, LT inverse square. So L square T power minus 2. That is equal to, here is also L square T power minus 2 plus LL. Here is a power 1, here is also a power 1. At the time of product of these two quantities, we have to add the powers. So L power 1 into L power 1. Here is also L square T power minus 2. Look at that. All the terms in that equation, all the terms in these equations are having the same dimensional formula. So this equation is homogeneity. This equation is dimensionally correct. If any one of this equation, all the terms which will be having that same dimensional formula or dimensional equation, this equation is said to be a homogeneity. In our textbook, they are giving one question. Find out that dimensional formula for that B. The question is, V is equal to A into T plus B into T square. What is the value of B? Now simply written as that A and B are the variable. It is not a physical quantity. It is a variable. Now for which physical quantity, if it will becomes at that place, this equation is homogeneity. We may ask like that. Or this equation is the homogeneity one. What will be the value for that B? It is a velocity. Okay. It is a time. T square. These are the time. In our book, they are asking what will be the value of B only they are asking. How we find? The dimensional formula for velocity is LT inverse. Okay. LT inverse. If this equation is a homogeneity one, all the terms they are having that same dimensional formula. This term having that dimensional formula. This term is also should have the dimensional formula of LT inverse. Likewise, this term is also should have the value of LT inverse. At the time only, this equation is said to be a homogeneity. Now, in our question, they are giving this equation is a homogeneity. Then find out the value of B. Now we are going to equating these terms. These two terms, equating these two terms. B T square is equal to LT inverse. What is the dimensional formula for the time? Is a capital T. So B into T square is equal to L T power minus 1. Then B is equal to LT inverse divided by T square. If the denominator, if went to the numerator, the power should be inverse. So that is equal to L T power inverse T power minus 2. At the time of product, the powers we have to add. So minus 1, minus 2 plus minus 2, that is equal to minus 3. So L T power minus 3. Now it is a dimensional formula for that variable B. So that's the question. That is present in our textbook. If they are asking that value for A into T is equal to L T inverse. then A is equal to, or the dimension for the time is a capital T. A into capital T is equal to LT inverse. So A is equal to LT inverse divided by T. So LT inverse T inverse, that is equal to LT power minus 2. Now it is the dimensional formula for the A. Okay, now there is a one more question. What is the dimensional formula for the B, or what is the dimensional formula for the A if the equation is a homogeneity one? Okay, then what are the applications? This dimensional analysis is used for which purpose? First application, one system of unit to another one system. That is easy to convert from one system of unit to another one system. One system of unit to another one system of units. Yes, this application only we are going to see. One system of unit to another one system of unit. How? What are the system of units? CGS, FPS, MKS. These are the system of units. For our convenient, different countries, they are following that system of unit. CGS means mass is measured in a gram and length is measured in centimeter. Now centimeter, that is the unit to measure the length. Gram, then second. If any one of the persons they follow these units, set of units, they should be follow that CGS system or Cartesian system. The CGS system is also called as the Cartesian system. FPS is the British system. British system, F is a foot, pound. Then second, for measuring the mass they follow that pound. Then to measure that length they follow that foot. Likewise, the meter, kilogram, and the second. So these are the different system of units we can follow. So using that dimension, we may convert the one system of unit to another one system. So at the time of converting one system of unit to another one system, what are the rules we have to follow? That's the first application. Then second application, we have to check whether giving the equation is dimensionally correct or not. Whether the equation is dimensionally correct or not. Then there is a relationship between the physical quantities. These are the three applications. First applications we are going to see about that how to convert that one system of unit to another one system with the help of example. So at the time of converting from one system of unit to another one system, what are the rules you have to follow? Then first is a rule. The product of n, the product of n is nothing but the numerical value. And corresponding units, the product of n and corresponding units is a constant. Corresponding units, that is denoted by u, that is a constant. Okay, that is a general rule. The product of the numerical value and the corresponding units u, that is equal to constant. For one system of units, the value is taken as that n1, In this system, the unit is taken as that U1. So the product of the numerical value N1 and the corresponding unit U1, that is equal to the product of numerical value N2 and the corresponding unit in another system. That will be the same. Look at that. At the time of convert from one system of unit to another one system, the product of n is nothing but the numerical value, u is nothing but the corresponding unit of what is physical quantity. The product of n and u, that will be a constant. At the time of that value of n and u in one system is denoted by the n1 and u1, another system that is the n2 and u2. These two values, they all should be same. Okay. Then addition to that, A for mass, here small letter A for mass, then B for length, and C for time. Now look at that. N1, okay, M1 power A, because I told A for mass, so the mass is raised by the power of A. Why I am put the value for 1? Because that value is the value of physical quantity in one system. L1 power B, T1 power C. That is a representation for that numerical value, representation for the physical quantity and the numerical value corresponding unit in one system of units. Then another system of units, the numerical value is denoted by that N2, M2 power A, because the unit that may be very far in the system, so that is the M2, L2 power B, then T2 power C. So that is that rules we have to follow. In this manner, you have to convert the system of unit from one to another. So the product of numerical value and a corresponding unit, that will be a constant. So of this physical quantity, either that will be in CGS or MKS, these two values, they are equal. So the product of N1 U1 is equal to that N2 and U2. To convert that physical quantity from one system to another system, the value does not change. The unit may be different, the numerical value then will be different, but these two quantities are same. How? 1 meter is equal to 100 centimeter. Now it is in the CGS, it is a MKS. That's a small example. In a MKS, this value is a 1 meter. The unit is a meter. But in the case of the CGS, the numerical value is 100. The unit is also a centimeter. But these two values are same. So that is a general equation. This is a general form. Just you have to understand is the 1 meter is equal to 100 centimeter. That's all. Okay. That's a theory. Then we are going to see about that example 1.12. How we convert the value of pressure, mercury pressure, from one system of unit to another one system. That's an example. Now simply the rules we have to follow. That's the easy one. Okay, clearly follow. Convert 76 centimeter of mercury pressure from CGS to MKS. And now this is the task. How you convert this value from one system of unit to another one system. First you should understand the question. What is the 76 centimeter of mercury pressure? 76 centimeter give how much pressure? Okay. Depends upon that liquid, the pressure is measured by that H rho G. So otherwise the pressure is measured by force per area. In this liquid pressure, the pressure exerted by that liquid, so rho is equal to P, pressure P is equal to H rho G. H is the height, rho is the density, G is the acceleration due to gravity. What's the value? How derive this equation? Height, that is equal to 76 centimeter. So 76, for understanding I am going to written this unit also. Centimeter. 76 centimeter is the height. Density. Density of mercury is 1.36 into 10 power 4 kilogram meters minus 3. It is the density of the mercury. In a CGS, now the question is given in the form of CGS. So the CGS, the kilogram we have to convert it into the gram. So kilogram, that will be written as that 1000 gram. So 1.36 into 10 power 4 into kilo is written as 10 power 3 gram. Okay, kilogram is written as 10 power 3 gram. Divided by meter power minus 3. So if it will become, the denominator is a meter cube. 1 meter is equal to 100 centimeter. Centimeter is a CGS. M is the meter. So the 1 meter is replaced by 100 centimeter. 100 centimeter or 10 power 2 centimeter. Okay. So 1 meter will be replaced with the help of a 10 power 2 centimeter. So I am going to replace 10 power 2 centimeter cube. Okay. Then we see is a 10 power 2 power 3. At the time of squaring, the powers we have to multiply. So this value is equal to 10 power 6. 10 power 6. If it will be comes to the numerator 1.36 into, if it comes to the numerator is a 10 power 6, already in 10 power 7 into 10 power minus 6. 10 power 7 into 10 power minus 6. So that is equal to 10 power 1. The 10 power 1 into 1.36, that is equal to 13.6. 13.6. The unit is that gram per centimeter cube. Just to see that the conversion, that's all. Into acceleration. Acceleration, G is equal to 9.8 meter second power minus 2. Here is a meter. 1 meter is equal to 100 centimeter. So if you replace that 1 meter is equal to 100 centimeter, 9.8 into 100 centimeter second power minus 2. So at the time of multiplication with that 100, that is equal to 980 centimeter second power minus 2. That is our question. So that is our question. Our question is what? Here is a centimeter, here 1 centimeter, here is a centimeter cube. So numerator, that is having the centimeter square, denominator centimeter cube. So the unit is 76 into 13.6 into 980 into 980. That will be having the numerical value. Numerical value in one system of units. Then gram, centimeter inverse second power minus 2. That is the equivalent unit for that pressure is equal to force per area. In a MKS system, force, the unit for force is a Newton and area is a meter square. So Newton meter power minus 2 is a unit for that MKS. But in CGS, the unit for force is a dyne area, that is denoted by the centimeter square. So dyne centimeter power minus 2 is the equivalent unit for that pressure in CGS. So we may written that equation 76 into 13.6 into 980, that is also equal unit, or otherwise written as dyne centimeter power minus 2. Now I am explaining the question only. Now it is the 76 centimeter of mercury pressure. Convert this value from CGS to MKS. That's a question. Pressure in CGS. So CGS gram. CGS is equal to 76 into 13.6 into 980 dyne centimeter power minus 2. Okay, that's the question. Now we are going to convert this pressure in CGS to pressure in MKS with the help of dimensional analysis. That's the application of the dimension. At the time of convert from one system of unit to another one system, we have to follow this general form. The general form is one system. Look at that. Pressure in CGS. Now what is the numerical value in CGS? Corresponding unit in CGS, M1 power A, L1 power B, T1 power C. And now it is a representation for that physical quantity in one system of unit. For clarity only I am put that CGS, or otherwise we may mention P1. P1 is that one system, P1, M1, L1, T1. That is the unit for one system. It is the numerical value for one system. Now it is in CGS, so I put that CGS. We converted into that MKS, so that is pressure in MKS. That only we have to find. The corresponding unit for MKS is that M2 power A, L2 power B and T2 power C. Okay, that's a general equation. Here in CGS, mass M1 is equal to 1 gram. Likewise, L1 is equal to 1 centimeter. T1 is equal to 1 second. Okay, in CGS, mass that is measured in gram, length is measured in centimeter, time is measured in second. So M1 is represented by 1 gram, L1 is equal to 1 centimeter, T1 is equal to 1 second. Here M2 MKS, M2 mass that is in kilogram, 1 kg. 1 kilogram is equal to 1000 gram. 1000 gram or 1000 is written as 10 power 3. Or that is equal to 10 power 3 gram. 1 kilogram, kilo is represented by the 10 power 3 prefix. Then L2 is a 1 meter. 1 meter is equal to 100 centimeter. Okay. 100 centimeter. 1 kilogram that will be written as 10 power 3 gram. Likewise, 1 meter is equal to 100 centimeter. 100 that is written as 10 power 2 is a centimeter. Likewise, T2 that is equal to 1 second. That is also 1 second. Yes or no? because MKS and CGS are having the same unit for the time. Here is a M1, L1, T1 value, here M2, L2, T2 values. Then we have to find out the value for ABC. Now what is the value for ABC? It's a pressure. Pressure is equal to force by area. Force is equal to mass into acceleration. So mass into acceleration divided by area. Area, that will be the area. Now the unit for the mass, kilogram. Unit for that acceleration, meter second power minus 2 divided by area is the meter square. Now I am cancelling this meter and meter square. So the unit for the pressure is kilogram, meter inverse, second power minus 2. Now what is the dimension formula? Dimension formula, mass. Kilogram, that's the unit for the mass. So the dimension for mass is M. And now that's the unit for length. So the dimension for length is L. L inverse. S is the unit for that time. So the dimension for the time is T. So T power minus 2. Now it is the dimension formula for the pressure. A for mass. So the power, no one power is present, that will be taken as a 1. So A for that mass. A for that mass, B for that length, and C for that time. Now I am going to equating the powers. From this equation, the value of M is equal to A is equal to 1, B is equal to minus 1, C is equal to minus 2. So I get the value A is equal to 1, B is equal to minus 1, C is equal to minus 2. General equation is that. Now I am going to convert from one system of unit to other one system. Look at that. This value only we have to know. So the pressure in MKS is equal to, okay, pressure in CGS powers M1 power A, L1 power B, T1 power C divided by, now this term that becomes denominator. So M2 power A, L2 power B, T2 power C. Okay. Then this value of pressure in CGS, that is equal to 76 into 13.6 into 980. So the value of pressure in MKS is equal to, the pressure in MKS is equal to, the value of pressure in CGS is 76 into 13.6 into 980. Then the value of M1 is equal to 1 gram. 1 gram divided by the value of M2. The value of M2 is equal to 10 power 3 gram. So 10 power 3 gram power A. The A is equal to 1. Okay. Then next term L1. L1 is the 1 centimeter. 1 centimeter divided by L2. L2 is equal to 10 power 2 centimeter. So 10 power 2 centimeter power B. So B is equal to minus 1. Then T1. T1, that is once again divided by T2 is also a once again power C. C C is that minus 2. Okay. The same units all get cancelled. Centimeter get cancelled. Second is a cancel. The product of this value is equal to 1.01 into 10 power 6. The product of this value is equal to 1.01 into 10 power 6. Look at that, 10 power 3. 10 power 3, if it will come numerator, 10 power minus 3. 10 power minus 3 into 1, minus 3 into 1, that is equal to the same 10 power minus 3. So the simplification of this value is equal to 10 power minus 3. Here 10 power minus 2, it will, when it will comes to the numerator, 10 power minus 2. 10 power minus 2 whole power of minus 1, that is equal to 10 power 2. 10 power minus 2 power minus 1, that is equal to 10 power 2. So I am going to written in that 10 power 2. Okay. Then it is both the numerator and denominator are get cancelled, power minus 2. So that is taken as that 1 power minus 2. It may be written as 1 by 1 square, that is equal to 1 by 1, because 1 square that is equal to 1. 1 by 1, that is also written as the 1. So into 1. This term is equal to 1. This term is equal to 10 square. This term is equal to the 10 power minus 3. Now the powers, at the time of multiplying, the powers we have to add. So 6 plus 2, 8. 8 minus 3, 5. So the pressure in MKS, that is equal to 1.01 into 10 power 5. Now it is converted into that MKS. After converted into that MKS, the unit, the equivalent unit is a Newton. Is a centimeter. The equivalent unit for MKS is a meter. So Newton meter per minus 2. Now that is a method which is using the dimensional analysis, how we convert from one system of unit to another one system. Thank you. Next class we see about that next topic, and it is also explained with the help of that several examples. Thank you.